Hello, everyone. Welcome back to
Hello.
Turing Complete, episode
It's been a
7.
while.
It has been a while. That was a combination of university, being sick, and our schedules not lining up. But we're back.
Joke's on you. I'm still sick.
Just stop being sick.
Physically impossible.
Yeah, apparently. Last time we completed the little box puzzle, which is for registers, and in Turing Complete, we received the component 256-byte register file. Now, we didn't build this in the episode, and so I did.
It's absolute mad.
So I do want to mention this design is definitely not mine. Okay, so this small section here, this part is 8 bytes. So 1, 2, 3, 4, 5, 6, 7, 8. That is I think built by mattbatwings, but that's where I found it. I don't know if it is his, but I'm going to assume that it is. What I did is just copy it to like in line with itself, and copy over a bunch of lines, and then copy it over an absolute ton of times, so that I end up with 256 bytes of storage, and I wired all the addressing to match that. So here currently this address is selected, which is why it is off. The rest is always on. And since we are selecting address 0, then this one is on. And if I were to, for example, flick this lever, then this line turns off, because that is address 1. And so we can store 256 different bytes of information. And this thing is it is very slow. As you can see, it takes a lot of repeaters for a signal to get all the way to the back. So if you were to write something to the last register 255, then it would take 4.1 seconds for you to be able to read from it. So if you write something to there and then try to read it, you pressing the read button will take 4 seconds for you to then see the result. I could have made this faster, but that's not the point of this. The point of this is we have it now.
And it works.
It works, and it's ridiculously large, and we are never, I think, going to actually use this thing. But it's there, and it's cool. So yeah, that's pretty much...
The thing is a maze with the size of it.
It's ridiculous, but I love it. It's really cool. So yeah, that's what I have been up to, and preparing for this episode a little bit. So Joshua, if you could come over here and stop jumping on the register file. Because I have things to explain for the next puzzle. Because the next puzzle is a decoder. A decoder, as we saw here, is a 1 to 2 decoder, or a 1-bit decoder, is simply just basically just a selector of which output you want to be on.
Yeah.
Right? So with 1 bit, you have on or off. That's 2 states. So you can have 2 possibilities. You can have output 0, I guess, and output 1 on. If you were to have 2 bits, well, now there's 4 possibilities. So you could have 0, 1, 2, or 3 on. If you have 3, then you could have 8. So let's go explain. As you can see, 0, 0 would mean that this one would be on. If I were to flick on this one, now I've selected 1. So then this one turns off, and I've selected this one, so that one gives an on signal. If I were to then select 2, then this one turns on, and that one off. And then finally, if I were to input both, then I've selected the 4th. Fantastic, thank you for the demonstration.
No problem. Happy to help.
So, if you were wondering, why is this useful? This would be a pretty good example. This is a 7-segment display, which I don't know if you remember, but back in 2021, I tried to build this.
Yeah.
Just using actual like logic gates and stuff, like ands and ors and nots and stuff like that.
I remember the frustrated typing.
Yeah, it was a 4-hour stream, and
Yep.
it at the end of it, it did not work, and I ended the stream with a /kill command and just ended it. I ended the stream. So anyway, I was not happy with that.
You succeeded now. Let's go.
It needed bug fixing, and this is so much easier than that was. So if I were to implement 0, if I were to input 0, as you can see, I've flicked none of the levers, then it...
Oh, I'm sorry.
Unflick it. Thank you. Then it displays 0. Now, if I were to hit 1, then it's 1. If I do 3, for example, it'll say 3. If I do 7, it says 7. If I do 6, then it's 6. And if I do 8,
it can count.
then it's 8.
Where's
So,
9?
The 9? That's here. Right, so the way this works is technically with a decoder and encoder. So, first off, we decode the number. Let's say we do 5, right? So, we have this one on and this one on. We decode into which line is supposed to be on with this green decoder. I will not delve too deep into how this works. Basically, all you need to know is that if the number is to be selected, then that line turns off because all the things powering it are off. So for the 5 line here, you can see there's a repeater that would power this line if this one would be on. But since it isn't on, the line is not powered. Here, there's a redstone torch that would power the line if the torch would be on, but it's being turned off by the line being active. Here, same thing with the repeater, and here, same thing with the redstone torch. So if I were to select 0, that would be this line, because all of them would power the line. So if I select 0, none of them are powering it, so the line turns off. Then here I have 1, then here 2. You kind of have to read it kind of like this, like vertically, I guess. So if there's a repeater, that is like a 0, and then a redstone torch is a 1. So here's a 1, a 2, a 3, then here you have a 4, the 5, which is the 4 and the 1 bit, then you have the 4 and the 2 bit making 6, the 4, the 2 and the 1 making 7, the 8 bit and the 8 bit with the 1 bit making 9. So if we go back to our example, we select 5, that'll make sure that the 5th line is off, meaning we turn on this line. So we've selected the line that says 5. And then what we do is we encode what we want to be on and what we want to be off. So if we want something to be off, we don't have to do anything, which is quite nice. But if we want to turn it on, we need to give it a repeater power output, like this. So for the 5, you want this line, this line, this line, this line, and this line to be on, because that is... If you wire it, I kind of wired it a bit messily here, but it's fine. That is what it looks like on a screen. That is all the orange circuit does here. It takes whatever number and powers whatever line needs to be powered for the number to show up. So that is an example of what you could use a decoder for. There are more examples, but we're not going to worry about that just now. So let's go over to Turing Complete. All right, so we are here in Turing Complete, and let's start with the decoder. With 3 bits of input, there are 8 combinations. Make a circuit that selects one output for each of the 8 combinations. No more or less than 1 bit should be on at a time. Perfect. So that is what I explained already. You have 3 bits, and each input dictates which combination there should be to turn it on.
Yeah.
I'm gonna guess that I have a bunch of different components. Fantastic. So I think the easiest way probably is to just make this with gates and just like and the I could use switches. That is smaller.
I think I also saw decoders there.
Wait, there's decode? Oh, right. There's 1 bit decoders. I'm so smart. Although I don't know if that necessarily helps. We'll see. There we go. Okay. So, if we want 0, then we're going to need a 3 AND of all the NOT signals. So I'm quickly just going to do this.
Wait, why are you mixing the knots and the yeses?
I'm not. I'm just doing this so that I can wire things together more easily. Oh my god. Okay, this is a bit of a mess, I admit.
I have to say this is criminal.
Yeah, it probably is.
And they're being the same color as well.
Yeah, that doesn't help, does it?
No.
Nah, it's fine. It'll be fine. Okay, so we want all the NOT signals. So I'll just take those like that. And then I will actually I need to invert that. And then that will go to there. Like that.
Yep.
So currently nothing is selected, so everything is fine. Then we want another 3 AND.
And then you're gonna do 3 ANDs and just not wild inputs each time.
Basically, yeah. 1, 2, 3, 4, 5, 6, 7. I wonder what like the intended solution is, because I doubt it's this one.
I can look what I have.
Sure.
Give me a second. Not saying that it's more optimized, but we can always have a look-see.
If I select all of them, then I want... Right, the opposite of this one. No.
Nope. I just did the same thing, but without the decoders.
Oh, okay. So you just did NOT gates, I guess?
I just did NOT and 3 ANDs.
Oh wait, this is supposed to be 3 OR, probably. Actually.
No, 3 AND.
Really?
You are correct. Yep.
No, but that does... No, because if it's a 3 AND...
No.
Then if I do this, then this is still on, even though this is incorrect.
Well, what's going on there?
Because it currently needs all of them. What?
Did you
Oh wait,
the NOT on the wrong side?
Wait, no, I see what I did.
No, you put the NOT gate on the wrong side.
I don't need the NOT gate there. That's the whole point. That's why I have the decoder.
Oh yeah.
Oh, I'm an idiot.
Sorry, I see. Yeah.
I just connected them wrong, accidentally. Yeah. So like this, then I don't need the NOT gate. There we go. So then if I want this one, then I need that. And then the NOT signals. Oh, great. And then this one to there. There we go. Oh wait, what's going wrong here? Oh wait, I'm stupid. There we go. Okay, now it should work. It's a pain, but it works.
Oh yeah.
Add a disable bit to this component. We were tired of looking at him running in circles. Okay. So now there's a 3-bit decoder with a disable bit. Okay.
Yes.
Cool. All right, let's go do that in Minecraft then. All right. Let's go do it. So a decoder. How do we build one?
Well, we already did once.
Yeah, that's a 1-bit decoder.
Want to just make this with 1-bit decoders into 3 ends? Or
No.
you have another way to do it?
Yeah, the way I just showed off there. That whole thing.
Yeah. Yeah, that checks out.
So we're just gonna lead these up. You can deal with inputs.
Yeah.
Give them like levers.
Yeah.
All right. So do you remember when we made like the ore? I think the byte ore. When we had the big.
Jog my memory real quick.
Sorry.
Jog my memory real quick.
The big grid thing.
Do you have any idea? Look behind you. Do you have any idea?
Yeah, I know it doesn't narrow things down at all, but here, look. This thing. This is essentially kind of what we're doing.
Yeah, I
grid
see
thing.
That.
See,
What
it's a
was
grid.
this thing?
This is the byte ore.
This was the byte ore.
Yeah. So it ores them, but now we're going to make a decoder to do something else. Namely, be a decoder. This thing is massive. That is insane. All right. So,
it feels like they're coming together. So like these people. It feels like I'm looking at a spaceship.
fair.
The size of it.
All right.
Feels like it's out of Star Wars.
All right. So, one, we're gonna put 2 blocks in between this time, because that's slightly better.
Okay. That's
So
4.
1,
That's
2, 3,
5.
4, 5, 6, 7, 8. Because we have 8 possibilities with our 3 bits. All right. So we extend this all the way to there.
Huh.
Yeah, you do that one. You are incredibly slow at this.
I wasn't at the right height, and I didn't want to adjust myself.
There we go. Now, as you'll notice, if I flick a lever, it's never going to reach the end. So we're going to have to fix that a little bit, but that's fine. We'll get to that later on. So, we want this to be line 0. This to be line 1, 2, 3, 4, 5, 6, and 7. Giving us 8 possibilities. You are terrible at line...
I'm too fast.
You suck at this. It's unbelievable. Okay, so this one needs to be...
Hey. Quack.
This one needs to be off.
Yeah.
Only when every lever is flicked up, meaning they're off. Right? So, wait, hang on. No, that's wrong.
No, that's right, no?
No. It needs to... Wait. So I need a repeater and I need a slab. Like this, like this, like this. Break those. Place a repeater. Like that. Get you to move out of the way. Like that. So now if anything is flicked there, this one is not off. What? Oh, did I... What? What's going on? Oh.
Oh.
I see.
Are they powering themselves?
Yeah. I forgot about that. There we go. There we go. Okay. So now if any lever is flicked, that line now turns on. And the thing is that we place
Shouldn't that line
at the end.
Oh.
And then that is the actual output. So now this one is selected, but then if I flick anything, then it's not selected.
Smart.
Right?
But
okay, so then the next line...
I'll start leading this into a genuine output.
Yeah, sure. I'll quickly wire these up. Okay, so this is obviously bit number 1. So we want 1 to be on. if this one is flicked. There we go. And then again with the repeaters to get the other part of it. So this extra block here is there to avoid back propagation. The repeater doesn't accidentally power the redstone line on top. So now if I flick this one, now that one turns off. And again, that one. And if I flick anything else, then both are off, because that's just wrong. So then here we have 2. We have 3 here. We have 4 there. We have 5 there. We have 6 there, and we have 7 there. And then everything where there's no redstone torch, we need to place a slab with repeater combo. Like that. You don't get it? Why don't you get it?
I don't really get what you're doing with the torches and the repeaters.
So the torches basically are a 1. So if there's a torch, that means I want that line to be on to get that combination. So here I have a torch, a repeater, meaning this one has to be on for this line to turn off.
Why do you want the line to turn off?
So that this torch turns on so that that one is selected.
And the repeater?
The repeater would power the line, stopping it from being selected. Because this is the wrong combination for 1. So, but if you look, this would be 3. So then that's the right combination for this one. I haven't set up this repeater yet, but if I put a repeater here, then you'll see that now only that one is on because that's the right combination for this one.
Right.
That's the point of it. So, yeah, repeaters everywhere where there's no torch. So there's no torch here.
Oh.
Did he spawn again? Oh my god.
Yep.
Stop inspecting my
they
redstone.
Keep wanting... They are just interested, okay? See them as like wandering scientists looking for the next new idea. Or geniuses to come up.
There we go. And that is almost it, just this back line now. There we go. There we go. Now this is almost complete. The only reason it isn't is because they don't reach the end. So what I'm going to do is I'm just going to take a repeater here, repeater there, and I think a repeater here with a block on top. And that should now fully reach the end, so now I can select anything. So if I want to select the 7 at the end, that one is now off, and again with the redstone torch at the end, then that one would be the only one that is on.
Are we gonna encase them in this machine? Would be funny.
I don't think we really can, because they can just walk off. It doesn't work there.
Yeah.
Whatever. So now, as you can see, we can now fully select any number we want. So if I have 1, then, or sorry, 0, then technically that one, you've numbered them wrong.
What?
These are not bits. These are not bits, dude.
Oh.
This is just output 0.
Sorry. My brain has gone so used to needing to label them as such.
even if you did it even if you did it that way, which you did, it's still wrong because one is on the left, one is on the right, not the left. It's clearly
don't need to call me out like this.
It's clearly been a while since you've done this. Right. So input 0 has been selected. Then input 1, input 2, input 3. Input 4, input 5, input 6, oh sorry, output, it's and then 7. So that's the 3-bit decoder. It's really not that complicated. This part is only so we can wire it to a display that is like in line with the inputs, but this is the actual decoder, this thing.
Yep.
So yeah, that's it.
Beautiful.
Easy.
Now, I know that we haven't gotten through all the ones in this arithmetic chapter. But do you want to go do the first one of the CPU architecture?
Wait, hang on. Which one is that? Registers.
It's registers.
What is that in? Ooh, I'm a bit curious. But I did kind of want to do the program counter.
Okay, yeah, that's fine. That's fine.
All right, let's go over to Turing Complete and we'll have a look. All right, so what is registered? Just so we time to create your own master project implementing the Overture computer architecture. Okay. Yeah, maybe not yet. We'll keep that for a future episode.
It's not as hard as it seems.
No, but let's stick to these things first, and then
the amount of
we'll move on
components you
from
can
there.
do it by are under 10.
That's fine, but for now we'll just deal with these first. I'm gonna guess Logic Engine. I'll do that next episode. Let's work on
I
counting first.
haven't even done that one yet.
Okay, counting is so fundamental. Even insects do it. You know what an insect is, okay? From counting, species can evolve to compare and do arithmetic, and before you know it, you have apes building computers. Make a device that counts increments once per tick. Build a counter that will increase. Yeah, okay. So, count, overwrite. Yeah, okay. So if this one is on, then we want to overwrite whatever it's counting, and if this is off, then it'll just increment by 1 for every tick. Yeah, that's pretty simple. Basically, all we need is an 8-bit register, because that holds the number that we're counting with, or we override it, we load it specifically with a new number. Wait, no, load is not it. It's save. My bad. Have you done this level already?
Yes, I have.
Okay.
This is one of the first ones that I really needed the help for, since my brain just didn't follow in the beginning.
Right. Okay. We have this value, and every clock tick we want to add 1. Not sure how I'm going to implement that just yet, but what we want to do is we want to be able to select between either what is being inputted or what this thing outputs. Presumably +1 first. That might be a smart idea. So I'm just going to make an adder. Oh, that is confusing. That is terrible. There we go, and add 1. It says no. Oh, that's terrible. So that is now 1. So that is the result. I don't need the carry, I think. So now I need to add a multiplexer. That goes in there. Every clock tick needs it always. I think it always just needs to load. There we go. And the question is whether or not it needs to save or not. Wait, no, it always needs to save. Every clock tick needs to save. Okay, so this one selects which one from the multiplexer it takes. I think, like that. And it is wrong. I need to select this one by default and get this one as a non-default. So if this is on, then it'll save 0. Otherwise, it'll... Yeah, okay. And then I need to make some kind of clock or whatever. This one can go to the output. So I can just...
Well, technically, there is a clock involved by like every
It's
piece
just
of instruction.
It's just an implicit clock, I guess, in this
Yeah.
thing. Okay, well, that's stupid.
Oh, if you think about it, the clock is already implicitly there because it goes through each of the instructions one by one.
Yeah, that's true. That's true. Okay, so basically what happens is, say I have a number, say I want to say 0, overwrite, then now it would put 0 in there if I do a step, but it probably overwrites my step. Yeah, and then it adds 1, but it currently outputs 0, and then I don't want anything to happen, so then it would add 1, add 2, and then, yeah. Okay, well, that's the counter. Let's do it in Minecraft. All right, so the nice thing here is we don't actually have an input except for a clock, really. I think we should make the clock an input, so that it's not constantly running. It's not always going at max speed. It's not constantly counting and overcounting. We are working with 8 bits, so that's going to be lovely. Yeah, let's do it. Let's start with the register, I reckon. So I'm just gonna do this.
May I request?
Wait, there's the input of the value. Yeah, okay, I'm an idiot. Never mind. There is inputs. Yeah, well.
May I request a 1 to 2 minute toilet break real quick?
Yeah, sure. Go ahead.
Yes.
Just get off that block, please. Thank you.
Very.
Yep. There we go. That's 4, 5, 6, 7, 8. Okay. So we can input any value, and then we want to be able to input whether or not we want to override, and then we should have a clock signal. Okay. So let's start with the multiplexer. And if the signal is on, we want this to be the input. So I think we do this. Yeah. And then we need glass. There we go. Wire that together. If I do this, wait, I can probably do this. Yeah. Save 1 byte.
Back.
Hello there.
What I miss?
I'm starting building the multiplexer.
There's one at the top or at the bottom?
What? One is at the bottom.
Perfect. I'll start labeling them. Do they need switches?
Yeah. Currently, everything needs a lever, and we will add 1 lamp, and that will probably be the clock. But I don't know yet where that will end up. So if this is on, then we want this to be propagated through. Yeah, nice. Okay. And if this is off, then it should not propagate. So then it should grab whatever value it has.
What's the left switch? How do you want me to call it?
Sorry?
What's the left input?
That's the selector.
Input?
That's the multiplex.
Selector.
That's the override or count. But just
override.
Selector.
Perfect.
Could you place torches on the side of these blocks? So like there.
Yes.
we go. And then this is the other. This is the other input. This is the count input. You can hold space and shift at the same time and to not go down.
Huh.
There we go. That's it.
Oh, there we go. Teamwork.
Place redstone dust on these blocks.
Yes, sir. Oh.
There we go. Done.
How dare you?
All right, and then we wire these together because they are specifically independent from each other. And I should be able to take a repeater output. And then I'm just going to copy this part up. Stack 7. There we go. There we go. And then I need this again. Cool. There we go. So that is the multiplexer done. Now we need to feed that into a register. That will be controlled by the clock, of course. It will always output, but it will not always save because we want it to work on clock output. Okay, so place some redstone dust like this. And then let's make the thing here. So actually make it green wool. There we go. Oh. These to lock it. And then
the override there, or?
Lime, hang on. We need here this to be the clock signal. This will tell the thing that it needs to save a new value, because we want to make it more manual, because we don't have an implicit. What are you doing?
I broke.
We don't have an implicit clock like Turing Complete does.
Yeah.
So we will just have to make the clock do it ourselves. So I will make this a...
Let's set some time between there, so it doesn't do it very fast.
What do you mean?
You're gonna make a clock, right?
No, I'm gonna make a red just a button.
Ah, okay. Oh, so we get to go through the steps each time.
Yeah, that we have full control over when it actually executes an instruction. You know?
Yep.
Place a lever. Cool.
Cool.
And technically, we want it to actually invert. So like that. There we go.
That reaches perfectly.
Yeah, it does. That's the nice thing about 8-bit registers in Minecraft.
Yeah.
Okay, so now we have the register, sorry. There we go. Now this needs to go into an adder where it constantly adds 1. Yeah. Thing is, I do know of an adder, I just don't know how to build it off the top of my head. Let's see if I can, actually. Oh, yeah, right. That's a thing. This does not work. What I can do, though, is that. Yeah, that was it. I believe that was it. There we go. Yeah, I believe that's it. So then all I need to do is supply this with a 1. And then whatever value we would fill in here, let's say I would fill in like a 4 right there. It will give me a 5. But if I were to power this as well... okay, yeah, I should move this torch a bit further away. But if I were to power the same side right there... Now it's 6. Because it added 1 to the 5, making it 6. So this thing works, is the main takeaway.
Perfect.
The only thing I need to do is quickly fix the torch placement.
And how do you want to handle the output?
So quickly place the torch there. 15, 14. There we go. The output here is these repeaters, which they need to. They are the output, obviously, of the counter, and or sorry, no, they're not even. The output is the register. So this thing just feeds back into the multiplexer. So it goes like this. I will world edit, don't worry.
I appreciate that very much.
Okay, and then it needs to feed back into that, which we'll probably do like over here. Quickly have to think of which combination I need of glass and wool. So if we have this, then I want this to be glass. Yeah, okay. So like that. All right. Okay. There we go. Stack a bunch of stuff. Then I want to stack this 6, I think. Oh, that's too much. Don't worry about that. And then we can simply wire this up to here. Wait, what went wrong? Oh, okay, right, my bad. Okay. Yeah, okay. There we go. And then all we need to do is place some redstone. Like that. Yep. And then connect it to the multiplexer. There we go. And that should do the trick. So now, as you can see, the register holds 0. So to add 1 to that, you get a result of 1 in the multiplexer. So if we were to get the clock tick and not do anything, then it would propagate this side. And it, as you can see, it technically does, but it needs an update. So we just need to click the button and it would count. And that should do the trick, I believe. So this is done.
Wait,
this is
should I
supposed to
make
be
it button?
a button. And I also want to make it slightly better as well. Oh. Yeah, okay. So this is, it already counted up to 3. It's a bit too quick. So I'm going to quickly improve this. I'm quickly going to temporarily place a torch there. And I'm going to make this a bit better. I'm gonna make this a pulse thing. Like this. Like that. into a block. Like that. And then I can remove this. And that should do the trick. So now it's on 3, right? We didn't build an output, but we don't really have to.
Where do I see output?
This would be the, I guess this would be the output here. So like, we can put some lamps here for now, if you want. Quickly wire some lamps here. Do you want some lamps? Okay.
We could.
Okay. Yeah. Yep. Nice. There you go. Okay, so now it has 3. And then if I click the pulse button, it'll count. It should at least. Wait, did it not work? Oh, it did. Okay, 5.
Yep.
Oh, okay, it's too quick. 7. What?
It skips one and then counts the second time that you click it.
Why? That doesn't make any sense. But it's still not working. But it is. What?
It's still only going by uneven numbers.
Oh, wait. Oh my god. Yeah, no, I get it. I get it.
What?
Still back propagation, basically.
Oh. How?
Yeah, okay, that's really stupid. How do I fix this part then? Okay, wait. So if I do this, and this, and this, and then this, and actually I don't actually need all these. Like that. And fix this. There we go. Now this should be the correct output. So basically, the torch, right? I placed a repeater before the lamps, right?
Yeah.
Like right there. The torch was still powering the back of the repeater, so it didn't matter. So it was still back propagating. So we were still done, basically. But now it should count properly. It worked.
There we go.
It works. I hate that you. I hate you.
Why?
The wooden button that you use. Wooden buttons are slower than stone buttons. Stop. Look how slow it is. No.
It's perfect. And on that note, it has been a very fun episode.
Oh my god. Alright, but it works. It counts.
Yeah. Oh, yeah. Oh, to win any argument. No, I lost my entire inventory.
Yeah, too bad.
Oh, how dare you?
There we go. We counted all the way up to 64 with our shenanigans. Alright. Editing Tristan here. I actually never tested out this program counter in full. We just tested the counting mechanism, which evidently works, but we never actually tested the override. So here we go. I will hit the override, so it will not select the counting option that's getting cancelled out, and it will select whatever I select here instead. And then if I hit the clock, then it should save that into the registers instead of the previous value +1. So now if I, for example, want to say start counting from 1 again, and I hit the clock button, then it goes back to 1. And now I can stop the override and hit the clock, and it will start counting again. And then let's say I want to count from 128, hit the clock button, it works. Thanks everyone for watching, and we will see you next time.
Bye.
Bye.